Today I will show you how to perform a brute force attack against the largest wallet holding currently 248,000 bitcoins, more than that, and it's worth thousands, millions, 25, more than 25 billion US dollar. And we're going to perform this attack in Rust. So first of all, let's initialize a Rust project. I will be using Z as the code editor. Perfect. No. Here we go. We have a fresh new Rust project. Basically what we want to do is create a command line tool where we can just perform execution in commands like cargo run, and then we provide the address. In our case it will be this one, for example. And when we do that, the attack starts and we perform different combinations until we eventually, hopefully, find the right private key to get access. To build this little command line tool, we will need the clap with the derive feature. Create a struct which will hold the command line arguments and make our lives easier with some macros. Let's quickly print them out and see if this works. Yeah, it works. Let's jump to the cracker and build this module which is supposed to will provide the target address, it will validate it and perform the attack. We can now interact with blockchain and use blockchain tools. We will include some crates which we'll need to interact with Bitcoin, and the big numbers we will now need to handle, because a normal unsigned integer 128 will not work. So we've added the BDK Bitcoin Development Kit wallet. Now we are gonna add BigUInt to handle these big integers. Maybe a typo here, and some traits for BigUInt which will make our life easier. Good. Now we should have access to the address as well as networked checked. Perfect. What is the next function that we're gonna implement is a public function new. We will receive a target address, which in this case is going to be just a usual normal string, and we want to perform the validation of the string inside this function. I'll just use unwrap, so if you want to make this safe in the future, feel free to do so and to properly handle errors, but I don't care right now. Here. And we will require the Bitcoin network, not some kind of testnet or any other network. Good. Now we can move on to our crack function, implement it later. What kind of helper functions are we going to probably need? So first of all, we probably need a way to generate a mnemonic, and then we need a function which will check this mnemonic and derive the addresses and then compare against the address that we've just provided to the cracker. And as a result, we expect a Boolean value. We will just use unwrap very extensively, which is not good practice, but for the sake of simplicity of this tutorial, we will leave error handling for whoever feels like to use this tool in production. Now we will need some kind of upper boundary of how far do we want to go, because, well, in BIP39 we have a huge amount of space, a huge amount of entropy. We can combine the words which are behind BIP39, which I will show in shortly, to create these unique, random and secure passwords. Yeah, so basically we have these words, and if you've ever created a Bitcoin wallet, you will be probably familiar with them. There are 12 or 24. This is a common number what people use, and you remember and write them down, and every one of these words has I think 11 bits value behind them, which it represents. So, but instead of shuffling these words, which is not very efficient, and there's always a checksum, so one of these words is a checksum, which will cause that when we shuffle them, for example 12 words, a lot of them will just fail because the checksum will not add up. What we will do instead is use one of the functions which BDK provides to create a private key out of an entropy. So it will be like 256 bits of entropy data, and at first, for example, just zeros, and then we will increment it by 1, and then again by 1, and again by 1. This can be represented as a mnemonic as well. But to do so, we need an upper boundary. And how many addresses how many options are there? So basically, let's assume that we have 24 words, and they can, one word can appear multiple times, which leaves us with, 256 bits of entropy, but 2 to the power of 256 possibilities. But we subtract 1 because there's 0 as well. So what is our max entropy? It is, correctly, but not really. We have to represent, if we execute now this code, it will probably fail, because this is going to be such a large number which cannot be represented in unsigned integer holding 128 bits. Let's see it in action. Yeah, attempt to multiply with overflow. So what we are going to use instead is a BigUInt, right, new 64, unsigned 64, and for example 2, unsigned 64. Yeah, then to the power of 256 and minus 1. But minus 1 won't work because this is a different data type. We'll need to convert this as well to a BigUInt. Good. Now we save the max entropy in our struct. And the idea is now to iterate until we hit this upper boundary, theoretically. Alright, in case if we pass the mnemonic to this function, it's going to compare it. In case if it's true and we landed a hit, then we're gonna print out a statement and we found a mnemonic and print a mnemonic as well, which is holding the amount of Bitcoin. Alright, let's take a look at the generate mnemonic function. We will need to pass a kind of entropy into it to generate a mnemonic out of it and a private key. So what we're going to pass is some kind of entropy, which is going to be a reference, a pointer to our BigUInt. In our case, we can pass the attempt, and out of it we will generate, we will increment it and then generate our private key. The BDK library provides us with mnemonic struct, and we can create with here this function, which is from entropy, that expects a vector reference holding always 8-bit. Here we can see we create a new mnemonic, English language mnemonic in the given entropy. The entropy must be a multiple of 32. So 4 bytes, and between 128 and 256 bits in length. We will create 256 bits mnemonic. So let's create such a long array. It's now 32 elements long, and it's always holding 8 bits. Now we get our entropy bytes and save them here in the entropy bytes variable, and we need to calculate an offset, because we cannot simply now take, for example, we have to populate our entropy bytes into the fixed length entropy, and we want to start from the end of the array and then populate it, not completely the end, but we want to take the entropy and put it at the end of our fixed length entropy array. An example would be, for example, we start with entropy bytes 1, just 1 bit, so it has a length of 1. We subtract 32 minus 1, we have 31, so we have our offset of 31. Now it starts populating at 31 and goes to the end, which is 31 in this case as well. And we put the entropy bytes, so we put the entropy byte at position 31. If we would have a length of 2, for example, we would first put it at 30, position 30, and then 31. So we were able to now create the mnemonic. Now we can compare it with our address. First, we need to derive the private key out of the mnemonic, then derive public key, and out of the public key we can create the addresses. This is our engine to execute signature operations. And for simplicity, we're just gonna iterate 24 times for our hard-coded derivation path. Good. So now we got a string, and now we will construct the derivation path struct. Now let's derive the private key and the public key. And for simplicity, we'll use pay to witness private key hash. Pay to witness private key hash. Now, if the derived address is the target address, then we return true. Otherwise, we keep iterating till we reach 24. And afterwards, we can return false because we couldn't find the right address. Perfect. Now, we don't want to log every attempt, but let's log like every 100 seeds and to see our progress. And for simplicity, we can extract this into a function, maybe log function, where we will pass the attempt and decide if we want to log it or not. In the rare case that we want to log it, we as well will need the mnemonic. I think that's it. Let's try it out. Yes. So it does work, but to be fair, we don't really need the mnemonic here because we just logged the result and don't really need to know what the mnemonic is in this case. It's just important to find out as soon as we land a hit. And what might be interesting is to see now how in fact, let's leave it for now and see how the mnemonic looks like if we print it into a string. Yeah, because now it represents some kind of words which we normally are used to. And he keeps incrementing it. And now we got add and bike, and then eventually it will increase this one, and then this one, and this one, and this one, and so on. Good. And what kind of addresses? So now we can remove it. Now we don't want to log the mnemonic anymore. And how do the addresses look like? Yeah, here we go, that's it. What you can now see is first thing that I simplified. The addresses don't really match with the address that I've shown earlier, because this one uses a different format. And we can as well here have a quick look. The address we are trying to get into uses a 3, which is a SegWit. As we can see, we have always BC in front of the address, which means we are our native SegWit address. To fix this, we would simply have to derive another address, but it would make things a little bit more complicated than they really need to be. More shortly. What we could do now is, for example, to check our speed of execution. Because right now we just can see that we are driving addresses, but we don't know at what kind of speed we do this. So everything more is now some kind of tweak to make the user experience a little bit better. What we could do in this case is, for example, as soon as we start driving the addresses and creating them in the mnemonics, we can start a timer. And then pass this timer into our maybe log function. Now every time we print the attempt, we can compare the current time with the time since we started the timer. Then we get the elapsed time. And this is packed handy inside a function for us. After we perform the printing statement, we can initialize start time with a new instant now to reset the timer. Yeah, so this working. The first one is obviously wrong. Thus we can generate around 16 seeds per second. Let's write a few tests just to check if it is really correct. We could, for example, now print a derived address. Let's, for example, get the first one. Check if our code works by running it against this wallet, against this address. To do so, we are now going to return our true/false value out of the crack function. Oh no, we don't have to provide any parameters now because we just run the tests. Cargo test. This means it won't find it. So we can turn this into strings as well. Nope. So the first addresses which we derived is this one. So we can test against, we can run a test if our cracker will find it. Cargo test, and found it. What about some other address, the 10th address? We will copy the test, call it just test track 2, paste the 10th address inside, and again run cargo test, and both tests worked. This is brilliant, perfect, great. So this is basically it. Now one question might remain: how can we increase the speed? For example, by just compiling it, we make it already a lot faster. So yeah, I don't want to print addresses anymore because it makes our program slower. And we can now run cargo, think release. No. I think I know. Cargo build release. Yeah, that's how it went. Now I've got this target folder. You can cd into it. We have a release folder, and inside the release folder we have, for example, Bitcoin wallet cracker, a binary. Let's run it. And we can see it. We are way faster now by just compiling it to release version. Previously we've been checking 16 seeds per second. Now we're checking around 250 seeds per second. We can now make it a little bit more prettier to look more hacky. Let's implement that. To do so, we will add a few crates. The console crate. And indicat crate. Good. Let's introduce a few emojis as well. we want to receive constant updates. So we'll create a new internal private function which will set up our console spinner for us. We want to call this setup spinner function inside our crack entry function. And as soon as we land a match, we now want to use this progress bar instead of just printing out the message. Or maybe log function can be now prettified as well. Instead of just logging it into the console, we'll use this progress bar as well. Good. Now it does look a little bit better, but we have here a little bug that always the Bitcoin wallet cracker gets print every round. We iterate through 100 seeds, which is something I would like to avoid. Let's fix that. Good. So the only thing that I removed was here the maybe log and the attempt. So that's something I forgot to remove. Now after removing it, it never works again. Let's build it, create binary out of it and run again. Brilliant. So that's basically it. We are running our brute force attack. Here we can see how many seeds per second we are able to check, and on the left the total number of seeds we already went through. Now, how long do we have to wait until we can find any address which is holding Bitcoin? Basically not possible, right? With so many options there are so many addresses out there in Bitcoin that it's not feasible, and for us humans to understand how large of a number it is and how many billions of years it would take, for example, for this computer or even Google Cloud servers find address which is holding any kind of Bitcoin. And we're not searching for any address holding Bitcoin, but we're searching for a very specific address holding Bitcoin. There's this brilliant article, how likely it is that someone could guess your Bitcoin private key. And here we can see a little bit more of numbers and how unlikely it is for anyone to find by accident a private key which is already has been used by someone else previously. For example, here we've got there are 6.8 multiplied by 10 to the power of 33 less Bitcoin addresses than atoms in the universe. Yeah, these are just numbers, and he's playing a little bit around just how unlikely it is and how this kind of brute force attack is not possible perform. Just for theoretical example, I think it's fine. You could see how BDK create works, how it's possible to derive addresses, to randomly create addresses from entropy. And if you're still interested, you can check out the GitHub repo. I will link inside the description where you can download this tool for yourself and play a little bit around with it and create your own variations. I hope it was helpful to see a little bit how this works in Rust, how we can create and try to theoretically crack these addresses. If we would have unlimited time, then it would eventually work, but maybe not with this setup, which was just for as an example. There are a few limitations, like for example the derivation path which we are using. It could be a different derivation path or that we're using public to witness private key hashes, which is a different address type which we are deriving than the one which is used by the Binance Cold Wallet. They use a SegWit address. Nevertheless, I hope it was illustrative and helpful to see and made a little bit, brought a little bit joy. Thank you.